Who of you is working on some IoT projects? Okay, at least some. Perfect.
But for the manufacturing clients, I'm pretty sure that many here.
Okay, who is a consultant for manufacturing topics? Okay, perfect. So that's me as well. So I'm in the manufacturing team at SAS, and for my background, I'm a mathematician, and since 5 years, I'm the pre-sales at SAS, and we're in contact with a lot of manufacturing companies when it comes to analytics. And therefore, I was at the conference, and where can I put? I haven't used this before. Okay, perfect. So the last month, I was personally involved in a family project. It was called How Can I Build a House? And when you start trying to build a house, there are a lot of different aspects you have to keep in mind. So first, you need a property. Then you need a notary for all the things around. Then you need someone who can build the house for you. You need an architect, and of course, you need a bank who will give you the money. So completely different aspects, but everything has to fit together perfectly at the end so that you will get a house. And if you're planning an IoT project or a kind of analytics project in the manufacturing area, it's slightly the same, or it is named the same sometimes or often. It's the same. So you have a lot of different aspects. Oh, I need the micro. I'm not used to it. Okay, I will try to think of it. You will have completely different aspects. And that was really interesting seeing the last 3 days, because it was a really busy conference with a lot of parallel streams there. And every talk covered one of these aspects. So one really big aspect in the market right now is it is there for years, but it's still there. It's what kind of use cases do we have, and what kind of use cases are really business cases, so that it is reasonable to start with an IoT project. So I've heard a lot of customers so everyone wants to do something with analytics because it's very popular. Everywhere you hear something about analytics, data mining, machine learning, artificial intelligence, and everyone thought that it could be really easy to use it and that it's the answer to everything. And I have the feeling that nowadays companies realize that it's still a little bit effort to doing some analytics. And you have to keep in mind if your use case you want to analyze is really a business case, so that you will keep on going with the modeling and putting some analytics into your company. So this is one really big aspect. Another aspect where a lot of discussions were going on is about the change management. So how can I transfer my organization to a point where we rely on the data, where we rely on some modeling results. And it's not just when we talk about some really sophisticated neural networks, which are really complicated and so on, it just starts with some simple regression or I don't know, decision trees or something like that, where the people have to rely on. And it's quite hard if they are not used to it. And so that's another aspect which is really important here. And there's, of course, how can I schedule such a project? Of course, what kind of hardware do I need? So what kind of sensors? How can I put the connectivity into work? So that's a really, really big topic right now. And then the analytics is just slightly covered. But it was my talk. It was just about analytics and about some algorithms you will need for analyzing your IoT data. So we also had a booth at the conference, and we built up some robots. You can see one arm of this robot here at the right, and the robot arm is still moving. And what you can see here is we put 6 sensors on this robot, and the sensors measures the torque, for example, and the speed of the robots. So these are the data we will get from IoT equipment, from some sensors. And these data are quite different to data we have traditionally in our analytics projects. And why are they different? So of course, you have seen that the data from IoT sensors or from sensors are generated in a really high frequency. So sometimes you have millions of records per second which are generated. And additionally, you will have a lot of different variables there. So sometimes a sensor generates thousands of variables just at one time. So it's a really big issue, the dimensionality which you have when you start doing such an analytics case here. The other thing is that most of the data are quite unknown so far. So it's not like in other areas where you gain your data, I don't know, since years, and you've done a lot of first analysis on these kind of data, and you will know how your data look like, for which use cases your data are suitable, and so on and so on. That's not the case with the IoT projects. There you will have a bunch of data and you don't know what to do with them. Next thing, maybe if you paid attention quite well, you have seen that at some time the robots didn't generate some values. So you will have a lot of missing values maybe in your sensor data. You have to you have to think about how will you handle these kind of missing data. You will also have some noise in your data. That's also something we don't have when we just look at customer data or something like that. So completely different. And then we will come to the point that we have the sensors at the edge, and there the data is generated, and you have to think how much of the data do I want to send back from the edge. And if they are sent back and you analyze them, you have to think about, or you have to define what kind of data and how much data do I want to store after my analysis. So what is reasonable to store? What is missing? The last point. And this is, of course, some imbalanced data which you have for, I would say, the most use cases you will find in the IoT area. So if you want to analyze the degradation of an asset, of an engine, for example, you will not have a lot of data of engines who degrades in the past, so that you can build up some classification models out of it. So you will just have the normal status of your engines. So they are working, they are running right now. And you have to define what is a defect on my engines. And that is completely different to some customer analytics, for example. If you're asking yourself which customer is interested in a product and who isn't, then you will have a lot of customers who are interested or who were interested in the past, and you have a lot of customers who aren't interested in the product or who weren't interested in the product in the past, and so you could build a quite good classification model. And that's not the case for the most use cases in IoT data or Industry 4.0. And that's why looking for predictive power is also really, really hard. And when it comes to the modeling, so we've seen some of these things in the first two talks. It's a kind of a life cycle of these kind of models. And it's not just valid for analytic models, it's also valid for reports. First of all, you have to define your data. You have to integrate your data from different sources. You have to standardize them. It's a really, really big task for a data scientist. It's kind of boring at the beginning because it takes so long before you can start your modeling part, but it's really important. Afterwards, you will start to prepare your data so that you can do some analysis on them. And then the really fun part starts, and this is the discovery phase. So where you evaluate your data, where you explore your data, where you build some first relationships, and where you at the end build some predictive models, for example, or some other kind of models you will put into production afterwards. And this comes to our third phase, and you have seen it in the talk before, that so after the modeling phase, the fun part for a data scientist is over, at least, but it's the important phase for the business will just start, because the business will just gain some benefit out of the model if it could bring your model into production. And that is a really, really hard task, which is not so interesting for us as a data scientist, but which is really important if you want to bring some analytics into your company. So you have to think about, okay, how can I put or implement my model I found already into production? So I have to put it in some third-party systems, for example. I have to define where do I want to deploy my model. Is it more in a database? Is it in a batch job? Is it maybe on some streaming data? And then you have to keep actions on it. So what do you want to do if I don't know, if there's an upcoming defect on your assets? So how do you want to react on it? Which employees should be involved in this process? And at every time you have to validate your current model if it is still valid or not, because for when the time is going, the accuracy of your model will decrease. And so at one time you have to think of some retraining of your model, of bringing some completely new models into production and so on. So it's a kind of a life cycle, and then it will start right from the beginning. You will have some new data, you will have some new explorations, you will build some new models, and you will put it into production. And how does it look like if we have some IoT data? Then the IoT data will require some specific capabilities at every phase. So let's start with the data phase itself. So we have seen that we have a lot of different variables. We have values which are generated at a really, really high frequency. So we have a bunch of data. So for the data phase, we have to transform the data. We have to pre-process the data, so we need some special algorithms for pre-processing the data. We also need, for example, some filtering of the data and some intelligent filtering so that we can filter out the noise for the data, and we just bring the cleaned data in some further steps. Then there's another step, and I would say it's in between the data phase and the development phase, the discovery phase. Of course, we have to reduce the dimensionality. So we are used to doing it, and we know a lot of algorithms for doing it because we had to for a long time. But when it comes to IoT data, we have a lot more variables, so it's much more important as it was before to reduce the data. And we have the feature creation part. So how can I extract some features? And in my opinion, that is the most important point when it comes to the question if your model will be good or if it's not good. So right now there's a big hype about some really sophisticated data science algorithms, some deep learning networks, and so on and so on. And how can I automatically optimize my parameters for these sophisticated and complex models and so on. That's really, really fine to have it at the end of the process so that you will gain some kind of lift at the end. But it's really important, especially in the manufacturing and the IoT environment, to create the right features right at the beginning, to put it into your model. So because we have some time series data here, and there are a lot of different ways how you could aggregate your time series data, how you could create some features out of your time series data to put it as an input into your models. And in my opinion, that's the crucial part when you try to build some good models in this environment. And when it comes to the discovery phase, there's also something different. Of course, we have all our classifications algorithms here as well, our predictive models, but a lot of questions are just about monitoring the process or the asset degradation, for example, just to monitor it and to detect when the degradation starts. And of course, we will have a lot of anomaly detection tasks which we have to fulfill. And this means that we don't, or that we're not able to build a classification model because our database is not suitable for that. And in the deployment phase, there's one really big change because we need a new approach. So I will show you later on how this could look like. But we need a new approach to deploy our models. Now we have streaming data, and it's not possible to put all your streaming data back to, I don't know, somewhere where you can build your model, where you can deploy your model and play everything back. So you have to think about a new way to deploy your model, and that means you have to deploy it directly at the edge or in the stream. And therefore, we need some new analytics techniques. And I've prepared 3 examples for you just to show it to you, how these different algorithms could work. The first example, I have to change this. So let's assume we are in a hospital, in a medical center, and we want to detect some asthma attacks. So what we can do, we can analyze the breath data of the patient. And of course, it's a time series data, as you can see it here. And on time series data, you can do a Fourier transformation. So you transform your data from a time domain to a frequency domain. So that's not pretty new at the moment. But what you could also do is just to work with a frequency. So let's just divide the whole range of the time series in some different buckets. and just do the Fourier transformation on each of these buckets. And then you can just detect or just analyze the frequencies of each bucket and follow them, how they will change. And we have done that with the breath data. And here on the left side, you will see the breath of a normal breath, the patient of a normal breath. On the right side, you will see some breathing data. On the x-axis, you will have the time, so the window which is moving forward. On the y-axis, you will see the frequencies of the Fourier transformation, and the color indicates the coefficient of the related frequency. And as you can see here, just by visualization and a transformation before, you can easily detect when a patient has an upcoming asthma effect or not. And you can go one step further and you can put the coefficient into a predictive model or doing some further analysis. That means that the short-time Fourier transformation is also suitable as a feature creation algorithm at this time. My second example is about a solar park. Here the task was to forecast the energy which is produced in the next hours. And there we had 77 variables. Variables about the weather, variables which describe some solar panel characteristics. And we have had them on an hourly basis. But before we start our forecasting task or our prediction task, we had to clean the data. And we have done that with an algorithm called robust principal component analysis. It's slightly different to a common principal component analysis, because what is the algorithm doing in the first step? So you will see our input data are some hourly basis data, and we have for each hour we have some characteristics on the weather and the solar panel. And then the robust principal component analysis divides these data, this matrix, into two matrices, one lower rank matrix and one sparse matrix. On the left, you can see the lower rank matrix, and this matrix represents the cleaned data. And on the right side, it's just a summation. You will see how the clean data deviates from, or the original data deviates from the cleaned data. And now you can work with a sparse matrix afterwards. And you can use it for two different things. Because in the sparse matrix, you will have some noise and anomalies. So let's start with the noise. If the value is just slightly above or below 0, you could put a threshold there, and you can say, okay, if it's just around the 0, it is kind of noise, I can eliminate it. And then you can eliminate it automatically if you define this threshold, just with this algorithm. And you can have a look on the anomalies and detect some anomalies here, because if the value is really high, and in this example, it's, for example, almost 4, then you can say it should be an anomaly at this time. And you can also see that if you do some visualization on this data and you will compare your produced energy with the forecast, and then you can also detect some outliers here, and they are well related to the high values in your sparse matrix. Okay, that was the first part, cleaning the data. Now we want to reduce the dimensionality of our variables. And we can also do this with a robust principal component analysis. So what we've seen here, we have our 77 original variables. And what we did as the first step was a normal principal component analysis. And that led us to a reduction of 66%. So we came up with 26 variables, which represents 95% of the variance. With a robust principal component analysis, you can do a principal component analysis just on the cleaned data. So that is the second step of this robust principal component analysis. And then you will see that we end up with a reduction of 83%. So with just 13 variables, it is possible to explain 95% of our variance for this task. So a really interesting result this time. You all know that principal component analysis are at the end a linear combination of the original variables, so there's not much interpretability. You can't interpret it at the end, and therefore it's sometimes not that easy, especially if you have to talk about your results and you have to talk to some other employees in your company who aren't aware of these kind of methods. And there's another algorithm, it's called variable clustering. And what is this algorithm doing? The algorithm is looking for some variables which behind in a quite similar way, which are really high correlated to each other, build some clusters for these highly correlated variables, and then take one representant of each cluster to do some analysis afterwards. So you will end up also just with, I don't know, a certain portion of your variables at the beginning, but you will have some original variables at the end, and you can talk about these kind of variables and can interpret them. And what you see here, so the colors are mixed up, unfortunately, but you can see here that we have done the same as we've seen on the principal component analysis with our data. So first of all, we did the variable clustering on our original data, and then we did the variable clustering on the cleans data by the robust principal component analysis. And then we can see that for a certain amount of clusters, we will get a much higher variance explained if we use the cleans data and do some variable clustering on the cleans data. So let's come to our third example. This is about engine degradation. Here the task was how can we detect some engine degradation, and that was the case I mentioned right at the beginning, where we didn't have a lot of data of engines who failed in the past. So we have to think about something which is suitable for anomaly detection. And one algorithm which is really suitable for that is a support vector data description, which we see here. And the algorithm is just putting some hypersphere around the data you have collected on some running machines. And you will see the support vectors, which are the blue circles around the hypersphere, and you will have a center of the hypersphere as well. And what you can do afterwards, you've built up these kind of models, you can score the models against new values, and you will get a distance for each state, a distance to this hypersphere. And then you can also say, okay, if the distance is just slightly above or below my hemisphere, it's a tolerance area, there's no degradation at this time, but if I will be far away from my hemisphere, then I will have an anomaly. So you can't specify the anomaly quite well, but you can say that now there's something going wrong. This could be an engine degradation, that could also be a process which is out of control. You can use it for different things. And we've done that for a data set which is provided by NASA about I think it was about 200 engines, and they ran them till the end of their lives. And we trained the support vector data description on 25% of the engines, and then we deployed our model to the rest of them, and these are 4 randomly chosen engines, but we've seen the same effect on every engine we deployed our support vector description. And what you can see here is on the x-axis you have the cycle of flight, and on the y-axis you have the distance to our support vector data description hemisphere, which we've built before. And then you can see at the first time the distance is very low, and then at a certain time the distance increases. And what you can also see that it's not just the distance itself, it's also the volatility. So at the beginning the volatility was really low, and then the volatility gets greater and greater and greater. This is just the output of the support vector data description. But then you can think, what would you like to do with this output? And there are 2 possible tasks. For example, you can define a threshold and define an automatic flag to alert someone when this flag is reached, or this threshold is reached, and send a flag. You can do this with the original distances, Or you can do it on a moving average, for example, to build a more robust alert at this time. And you can also use this kind of algorithms for filtering. So if there is a really high, or a value with a really high distance at some time, and you see that the values around are not that high, you could probably interpret it as a value which is not reasonable and filter it out. So again, many ways where you can use this kind of algorithm. And let's come to our last step in our analytics life cycle, the deployment. And this is the deployment, how it took place traditionally. So you will have some data, you will put your data into a data storage, you will build some or define some ETL processes around it, and then you will do some modeling, some reporting, some modeling on this data in your data storage. You will get some results, some deployment, or some alerts out of your model, and this is as it was in the past. So maybe if you have a lot of data and you want to get some really fast results, you put the model into your database to run it directly in the database. And now you could put your streaming data just in your data storage as you have done it with your normal data before. But that's not the recommended way, and it's not the way how it will work out. So you have to think about different approaches for deploying your model. And as you can see here, this is our recommended architecture from a really high level, how the analytics could take place when it comes to IoT data. So you will see, you will have all the items from the slide before. You will have your data, you will have your data storage for these data, you will have some ETL processes. You will have the chance to train some model in the data storage or with the data from the data storage and to deploy it there. So everything which is known is right there right now. But for the streaming data, you will put a different stream or a different part. So the streaming data will not go to your data storage. The streaming data will have their own place. And you can see that now there are different approaches where you can train your model and how you can deploy your model. So for example, you can train your model offline in your data storage and you just deploy your model directly on the stream or at the edge so that all of your streaming data are scored by this model at the edge. Or you can go one step further and train your model also directly at the edge or with your streaming data. And that is really important when you have to retrain your model a lot, because then you don't have to put your streaming data in a data storage, retrain it, and put it back. You can build the whole life cycle in the streaming data. And that's quite important. And then out of the streaming data, you can do some reporting, some alerting on whatever you need. Automatically decision, that's really open. Okay, and that is my final slide. What I would like you to remember when you think of our talk today, it's when it comes to IoT data, you will need some new analytics techniques to analyze them, to bring some really good outputs. And you will have to think about a new way to deploy the models, because now you have a bunch of streaming data, and this is slightly different as we have known it before. Okay, thank you.